Okay, this is going to be AP Statistics. In the textbook, this is going to be section 10.1 for the current textbook. We're going to be looking at a two proportion significance test. So let's get right into an example here. And let's set this up here. This way. Here we go. So we have some data about our teenagers going deaf. So in a study of 3,000 randomly selected teenagers, in 1988 to 1994, 15% showed some hearing loss. We did a similar study in 2005-2006 and found that 19.5% showed some hearing loss. So do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Okay, so clearly from the first study to the second study, there was definitely an increase in percentages. So the issue just is, can we prove it's significant statistically, or could it just be due to random chance? So that's what a significance test is going to do for us. We're going to get a p-value at the end, which is basically going to be how likely is it to get a sample or to get a difference that large if the null hypothesis is true. So let's get those statements set up. Whenever you're testing claims about two proportions, say your null hypothesis and your alternative, you always are going to assume, just like with one sample test, in the null hypothesis, there's always some sort of equality. So the same thing actually happens here. We're going to assume that P1 equals P2. Okay, and let's go ahead and define these. I'm going to say P1 is going to equal the proportion with hearing loss. Sorry, I'm running out of space there. In the first time frame, so in 1988 to 1994. Okay, and I'm going to call P2 going to be the second group here, the proportion with hearing loss in 2005-2006. And we're going to basically see, is there a difference in these groups, to kind of show if the percentage has increased over time. So that's the defining the parameters part. It's very important. Okay, so that's one way to write the HO. The other option would be, alternatively, if you think about just subtracting P2 from both sides, you could write your HO that way, where P1 minus P2 equals 0, and that would actually give us a little more visual if we're drawing the curve of the differences in a minute here. We could see the centers at 0. So either way you want to write those is fine. Now the alternative, do we think that this has increased? Okay, so we want to make some statement about P1 and P2. Okay, and if it's increased, that would mean that P2 is now larger than it was, before. The proportion of hearing loss is greater. So the way we write these, we usually just write P1 first. So this would have to be a less than in here to show that the proportion has increased. Okay, or again, the other option would be if you were to subtract P2 from both sides, you would have P1 minus P2 being less than 0. Okay, so you can decide how you like to write those. Either way, let's get our conditions checked just to make sure we can actually do a normal curve and go on with the problem. Okay, so let's get some information out of here. I'm going to kind of divide this up and get some numbers here. So I'm going to make this the what was the first one? 1988 through 1994, I believe it was. So it had a p hat given to us of 15%. They gave us a sample size N1 of 3,000. Okay, while in the other year, in 2005-2006, which we are calling P2 basically, so its sample proportion at that time was up to 19.5, 0.195, and its N, to give a subscript 2, was 1,800. Okay, so what might be helpful, especially when we get into the calculator method in a second here, we need to know a number of successes, okay, which the calculator calls X, which is basically how many people suffered hearing loss in each of these times. So it's just a simple multiplication problem. It's going to actually end up being 0.15, so it's like 15% of 3,000, right, just to get a number here. So for in that case, it turns out to be 450. Okay, so the proportion was, or the fraction would be 450 out of 3,000. That would get us the 0.15. And similarly over here, 19.5% of 1,800 would give us a count value of 351. Okay, now I may have rounded it. I can't remember if this came out to be a perfect whole number. If not, if it's a decimal, you need to round it to a whole number to use the calculator. Okay, those x's need to be integer numbers only. Okay, so that's going to make checking these conditions a little bit easier, I think, to have all that in front of us. So let's check the conditions here. Okay, so the conditions to do a test, I mean, we need randomness. Okay, and I know in the problem they did mention that both samples were taken randomly, so that's big. Okay, um, so that's kind of a check mark. You can just say they told us in the problem. We're going to need independence. Okay, and that's something a lot of times needs to be assumed. We're going to assume population, let's say both populations, right, because we're dealing with more than one, are greater than 10n. Okay, I think that's a pretty safe assumption. Okay, if n was 4,500 or 3,000 and the other n was 1,800, I'm assuming there's more than 10 times that number of teenagers in each of those years. Okay, and then the other one is the randomness now, or I'm sorry, the normalness. We cannot assume that. That's the one you actually have to show some calculations for. And it's going to come from using n times p in both cases, actually. So you're going to need to check that, and you need to show this step. Show me that basically the number of successes, we actually know that. So that's 450. So in the first group, there was 456 successes. So for group one, which is the first time frame, we know there's 450 successes. This is the same as doing n times p. And that would mean then how many failures would there be if there's 3,000 total? So that would be what, 2,550 considered failures, meaning they did not suffer hearing loss. So just the way we're wording it. But that's basically what your n times 1 minus p would be. Okay, so just make sure we're clear where those came from. This is just n1 times p1, and this is n1 times 1 minus p hat 1. Okay, and those are both greater than 10. Similarly with the other group, group 2, we can see that there was 351 successes. So if there was 1,800 total, there's clearly more than 10 failures as well. So make sure you mention both of those. I'm just saving a second here to not show that, but those have to be written out. Okay, so we have our normal condition, which means we can draw the normal curve. We know it's random. We have our independence, so we can do our test. Okay, so let's set this up manually, and then we'll kind of show how to do some of this on the calculator. So basically, what this boils down to, if you think about, and I'm just going to do this briefly, in group 1, so this was back in the first time frame, 1988, all samples would vary around, their mean at that time was 0.15. That was the p hat from that population. Okay, and group 2 had its own little distribution. If you were to think about the sampling distribution, it would vary around 0.195. And each of these things have their own standard deviations, which we have a formula for, which would be this. Okay, so this would be the standard error, right, for the first one. And the second one would be same thing. Okay, and of course the 0.15, that would be the p hat. And then the n for this case was 3,000. So we could do the calculation and do something similar with group 2. Now here's where it's a little bit different. When we combine these, okay, and we're going to make a new one for P1 minus P2. Okay, when we combine these, the difference, okay, the center here is not just the difference from our curves we drew above. Okay, if we were doing a confidence interval, it kind of is more like that, but this is a little different. If you remember, our original claim from the null hypothesis was that P1 equals P2, right? So we're assuming that's true. So if we assume that's true, we actually would assume that the center would be at 0 here. Okay. Now our samples had a difference of what? If we did the sample values, it'd be 0.15 minus 0.195. So this is the difference from sample to other sample, and that was negative 0.045. Okay, negative sign in there. So that's over here somewhere. Okay, so we fit that in based on assuming that the mean difference, or the difference in the proportions, I should say, is 0. So what the question becomes now is, it looks like a normal CDF. We're going to try and calculate a p-value out here. But what are we using for a standard deviation? Okay, we know the mean is 0. We know the upper bound's the negative 0.045. But the other thing's the standard error here. And it's a little different. With proportions, you cannot just simply do this one and square it, and then do one for this other curve and square it and add them together like we did for confidence intervals. Okay, and here's the reason. It goes back to, again, we're assuming P1 equals P2. So we're assuming that they actually have the same P hat. Because, HO, if HO is true, P1 is the same as P2. So what we do is we call this pooling these and we combine them together. So for the standard error, we're going to pool the two together, just combine them. So what we actually need is a P hat combined. Okay, so what we need to do for that is just going back to the original problem. Okay, that's why we wrote the X's and N's down. The number of successes combined, we're going to take this 450 plus this 351. Okay, and then the denominator is going to be the 3,000 plus the 1,800. We're just acting kind of like these came from one big pool. Okay, so let's figure what that is to get our p hat combined. It ends up being, again, 450. So the total number of successes plus 351 out of 3,000 plus 1,800. And if you do the quick calculation on that, you get around 0.16. Let's just round that to like 0.167. Okay, so that's the combined sample value from both groups combined or pooled. Okay, that's what we have to use to get the standard error for the differences here. Okay, so the standard error now, just like before, it's just going to be the square root. Okay, we're using this as our p hat in both pieces here. So that times 1 minus that over the first n. Okay, and then for the second piece, we're using that same p hat, and we're using the other n. Okay, so this will get us our standard error for the differences here. So be careful on the calculations. Again, I always suggest to break it into little pieces and maybe figure out this is some decimal first, it's gonna be some small number. Okay, this is gonna be some small number with maybe e to the negative something because it's a scientific notation. Small numbers. Add the highlighted pieces together, then take the square root, and I ended up with something around 0.008678 roughly, okay, and depending on the rounding, you may be a little bit different, but that's okay. Okay, so that's the standard deviation of the curve up here, the standard error, because we're talking about a sampling distribution. Okay, and that's going to allow us to do the final step here and do the normal CDF. Okay, so our p-value now, that tail area that we shaded right up here, okay, is basically saying how likely is it to get a sample like ours if the true difference is really 0. So we're finding that left tail area. It's going to be a normal CDF problem. We showed it's normal earlier. Okay, it's on the left, so negative 999 up to our value of negative 0.045. Okay, we had assumed the mean was 0 in the null hypothesis, and we just got our standard error here. Okay, so doing this should get us our answer. So you can go ahead and take a second and throw that in. And let's see what we get for a p-value here. If we do negative, and my calculator is giving me something like 1.079 e negative 7. Okay, again, with the rounding, you may be slightly different. But again, if you remember with this e negative means times 10 to the negative 7th power. So the quick way to do 10 to a power is move the decimal. Since it's negative, we're going to go left. So that decimal is going to go way over there. So this final answer is going to be 1, 2, 3, 4, 6 zeros, then the 1079. Okay, that's our p-value. Okay, seem like a pretty good probability or not? Pretty low, real low. Okay, so basically, since that p-value is so low, okay, let's write our conclusion here. Since p is less than alpha, right, that value is less than pretty much any alpha you'll ever see, we will reject HO. Okay, we're rejecting HO flat out. The probability was so low, I'm rejecting HO. Okay, so going back to our statements, what does that mean? So we can get a conclusion using context here. If we reject HO, okay, so we're rejecting this. Okay, so we actually believe we have evidence for HA. Okay, HO is rejected. So there is evidence that the proportion has increased. Okay, so based on this data, there is evidence. And this is the big part of the conclusion too. So there is evidence. And since we defined P1 and P2 earlier, we can just write it like this, that P1 is less than P2. Okay, or it might be safe just to say hearing loss has increased. Okay, or something like the proportion of. Okay, and that's it. There's your conclusion. Okay, so that's doing it manually. It's a little bit iffy with some of the pooling stuff that you need to remember and then the formulas and whatnot. But it does follow a lot of the same procedures. Okay, now doing this on the calculator is much, much faster, and I'm fine with you doing it, but you do need to know some of the background details. That's why I showed you manually first. But to do like the actual last couple steps on the calculator, here's what we can do. Since all the conditions were met, we are able to go to quit stat over to test. Okay, and again, the biggest thing is probably knowing which ones we're doing. So this one dealt with two proportions and it was a test. It's not a confidence interval. So there's one option here that says two proportion z-test. Okay, we're gonna go in there. It's gonna ask you for both x's and n's, so that's why it was good to have those figured out earlier. The first x was the 450. The first sample size was 3,000, so we wrote these down as soon as we started this problem, right? So notice there's no 15% and 19.5% in here. It's just counts and sample sizes. So that's 351 out of 1,800. Okay, the way we wrote our statements was that P1 was less than P2. Okay, and we're going to go ahead and you can either do calculate or draw. And it's going to go ahead and do this. I think the p-value is going to be slightly different. There's some random graph in there that we are graphing in pre-calc, but the p-value is not going to be exactly the same as what we got, and it's just from rounding. But the conclusion, I mean, look, this says it's 0. Okay, it's such a small number. Remember, we got the something times 10 to the negative 7. It's just saying it's basically 0. Here's your test statistic, which is actually important, which I'll mention that real briefly. Because a lot of times they'll want you to report both of those. But again, it's so small. I mean, it's way out here basically that you can't even see it. Okay, so that test statistic, just real quick to show you where that came from. With these tests, the test statistic, which is either a Z or a T, depending on your situation here. With proportions, it'll always be Z. Okay, remember with means, if you don't know the standard deviation of the population, you would use a T. But the basic setup, it's always statistic minus parameter over some sort of standard deviation. In this case, it's standard error because we're dealing with samples of different sizes. So basically, the statistic was what we got. That was the difference. Okay, so in this case, the statistic is the difference in the sample values. Right? Statistics come from samples. Okay, parameters come from populations. So that's basically the same thing without the hats on there, right? And then standard error, we had that big messy formula that we used. I'll just write it down, but we already did the calculations on it. Remember, it was the one using the combined over N1. P hat combined, 1 minus P hat combined over N2. And again, luckily we did that number already. We actually did all this, so I'm just showing you how it fits. So let's go through piece by piece. Let's find them. We already know our difference in our samples. That was the negative 0.045. That was just a subtraction problem. Okay, minus, what about this, this guy here? Do we know the population values? We don't. Okay, so I don't really know what to use for those, but if you remember, we are assuming from the null hypothesis that P1 equaled P2. Okay, so that would just mean that this whole thing would actually be 0. And that's good. That happens all the time with these type of problems. So that's just like minusing 0, so it's really not even there. And then the denominator, we did the calculation a couple pages ago, was 0.008678. Okay, and if we just do the division on there, that's going to get you your test statistic, which we had from before. So let's just do that real quick. If we did the negative 0.045, just a decimal point there, 0.045, and we divide by the standard error, which was 0.0086. Ah, got this new system, it's kind of lagging a little bit. Here we go, and that should get us our test statistic. And again, it's a touch different because we had rounded that standard error a little bit. So it was negative 4 point something on the graph. We got negative 5 point something. So I'll be able to tell if you set it up correctly, and I won't make a huge deal about the rounding. So okay, so I just want to show you how that all fit together. Again, use the calculator. It's there to be your friend. It's there to save you time. But there may always be some times where you need to know some details. So that's why I showed the background there. Alrighty.